system where I spell out for you that in fact there is one node A, one node B, right, with switch 1, switch 2, and switch 3 in between, right? Do you guys see what I'm drawing here?
Yeah. Oh,
Okay.
I actually didn't draw the 1, 2, 3. I just draw the switch symbol in between.
That's fine.
I guess that, yeah.
No, that's fine. Yeah, don't worry about it. I'm just looking because obviously, right? The more switches, the more time it takes to transmit the signal, right? Because it indicates longer distances and so on and so forth. Okay. So how do we do a problem like this? First of all, right? It's a circuit switch network, right? Which means, right away, I know the structure. In fact, the circuit switch network has a very defined structure, which means there's a setup time, there's some kind of data transfer phase, and then there's a teardown. True? Right? There are very distinct phases to a circuit switch network. Okay. In fact, right, what you do know, right, is that the overhead obviously is part of the setup, and when in this case, I tell you that the setup time. So remember, right, your way of solving this problem is that you're looking for this. You're looking for this time, and you're going to try to piece it together, right? What these times are. Okay. So because I already know that there's a setup time, right? So this is one piece of it, and then there's a teardown time, which is obviously this piece here. Right? So really then all I really need to figure out are these times used for data transmission. Okay. Well, setup time, I told you outright that in fact setup time, I'm just trying to find the right color to do this, right? Is denoted by X. And then I tell you that the teardown time is denoted by Z. So then you know your total time is X plus Z. And then plus something else, of course. True? Right, Bob?
Yeah, that's the first part.
Exactly, right? So you really know the only time that is in question, right, is this time here, right, for the data transfer phase. Well, as I said, your goal is to piece them up together with the information that you have. So obviously, there's some time that you can determine here, from here to here. Okay, and then obviously there's time that goes from one link to the next, one link to the next, one link to the next, one link to the next. So then your goal is to, okay, is there a time here? Is there time here? Is there time here? And obviously to the last piece. What is this time here?
You mean the definition?
Yeah.
The slope.
No. This height here. The time for this height.
Oh, the time for this height is just the time it takes to transfer the data, which is just T.
Exactly. Transmit time.
Yeah.
Okay. Then what are, so if you know, so the first bit through to the last bit, then the question is, what are these times here? What is the height of a slope? What does the height of the slope indicate? Anyone?
Propagation time.
Propagation time. Okay. So what is propagation time? It's denoted here by D. So there's one D, there's two Ds, there's three Ds, and there's four Ds. Right? And if you can piece it up together like this, right, then you have unique time segments to compute from start, right, which is here, all the way through to N, which is here. Right? So then you have a plus T and then plus obviously 4D. And then you go back and say, okay, does this make sense? Because obviously, right, there's a setup time, which I've accounted for, and there's a teardown. And I know in circuit switch networks, there are no queuing, right, or processing or waiting time associated with it. Then yes, obviously, there is transmit time, because I'm going to put the whole file, right? In this case, it's one single packet. But what changes in circuit switching is the number of hops I have. So this is one link, this is one link, this is one link, and this is one link. And it should be, right? If there are more links, which means indicates if they're all equal distance links, which means more distance. So the only thing that's really variable is this value here, 4. Because more links indicates longer distances. Longer distances obviously indicates, right, longer, right, in terms of propagation time. Okay. Any questions on the quiz?
Yeah, I missed the propagation time, I think.
Right. So, but does it? So the thing is, that as I said, right, you have to always go back and look at your solution. So if you did not write this, does it make sense that circuit switching is only a function of setup, teardown, and transmit time? So what you're telling me that if I have a circuit switch network transmitting the data between Vancouver and Richmond, has no difference in transmitting the time from Vancouver to Toronto. Does that make
Okay.
sense?
Yeah.
Right?
Yeah,
Because
that makes
obviously, right, the bits have to travel a certain distance.
Hmm.
Right? And the distance in this case, obviously, right, is based on the number. So you always want to go back and review your time, right? And say, is it truly, right, just only a function of the parameters I've stated? And as I said, right, it is on purpose that I gave you, all the bits and pieces pertaining, to this setup. Your goal, right, is to be able to understand the system enough so that you can now piece together the information that's necessary to determine time. Okay? Any questions on sort of the quiz? Any questions?
I guess I didn't really understand the meaning for propagation in general. So that was kind of like a little bit of confusion for me. I
Right.
didn't
But
quite
but,
understand
propag-
that.
but propagation, you do know the definition, right? Propagation is not a new concept for you.
Yeah.
Propagation is always a function of distance.
Yeah.
And I said, in this diagram called the space-time diagram, the x-axis denotes the space, which is distance, and the y-axis denotes time, right, which is the equivalent, right, of the time that you're trying to compute from start to end of any system.
Okay.
Okay?
Yeah.
Okay. So I want to spend a few minutes here on sort of the project. So you all of you should have received an email from me telling you that I've sort of released sort of the project description for you guys. Okay. Have you guys had a chance to read it yet?
I did.
Okay, so I want to give you guys 5 minutes to read this. Okay, so it's really on D2L, so you don't have to read off my screen here. So it's on. I want you guys to read it because it is important that you understand that what you're responsible for and what's expected of you. Okay, so all of you, right? Let's just take 5 minutes to read this, and then I'll go through with you what the highlights of this project is. Okay, so please go to D2L, read it in detail, and then I'll explain to you and take questions as necessary. Okay, so I'll give you guys 5 minutes to do that if you haven't already read it. If you already read it, maybe just either take a 5-minute break or just reread it again. Just make sure that you got the information correct.
Wow, I'm actually hyped for this final assignment. It's really interesting.
Right. Why though? Is that Chantel?
Yeah, sorry.
Yeah,
It's
okay.
probably because it's like a more look on a practical approach for the information we've been learning
Exactly.
throughout the course.
Yeah, exactly.
So
Yeah.
it's really exciting to be able to put it into use.
Yeah, so I'm going to talk about that in a second here. Right? So it's sort of as you said, there are many sort of different types of projects I could get you to do. But what I wanted to do was I wanted to take something that is real, which is obviously in your case, as you said, right, it's practical. But I want you to be able to sort of apply sort of what the key, I think, learning outcomes of this course is that you have like understanding of networks. But if we can extend it a little bit, which means, okay, I know there's a network, I know there's data that goes back and forth, right? From a computing perspective, right, what am I most concerned with? And one of the key issues obviously is around security, right? And the idea for obviously for you to sort of intercept data and information and so on and so forth, right? So I'll talk about it in a minute, okay, Chantel? But I hope you guys have fun to do it. And I'll talk about some of the requirements and how you be graded and assessed, right? And we'll go from there, okay? I just want everybody at least have a chance to read the lab, the description. Right. Okay, so it's 10:45, right? Is anybody still reading the description? I actually kept on purpose the description to be quite terse, which means that I didn't want you to overwhelm you with lots of details in terms of what the description is. But at least I hope, at least in the write-up, you are well aware of what you're responsible for and what the expectation is in terms of your deliverable. Any high-level questions first? Is the description somewhat clear in terms of what you need to deliver?
I do have a question. Are we allowed to choose the programming language?
Yes, exactly.
For our demo?
Yeah, exactly. Okay, so let me go through in terms of in a systematic way in terms of what I expect you to do with this. Okay, is that I'm putting into sort of the double screen just so that I can actually see it myself. So this is your final project. As I said, this is in lieu of your final exam. Okay, so I think that as the course progressed, I get more and more sense that there is sort of a preference, right, to have a project, right, over a sort of in-class final exam. It's not in-class, sorry, a final exam over proctorial. Okay, so the thoughts that I had, right, there were many different sort of ideas that I could have you do as a project, but as sort of responding to Chantel a few minutes ago, right? I wanted one that illustrates networks, right? And I wanted to go sort of, of course. But I wanted one that sort of extended a little bit so that you see more the practical side of how networks are, which means to do this project, right? My goal is that you will learn a lot from doing this project. Okay, that is, you're able to set up some kind of a communication going on, right, between two entities on the network. In this case, right, I want you to transfer some data. And then what I want you to be able to do, right, is as what is known as the man-in-the-middle attack, right, is that I want you to actually steal that data, which means in sort of technical terms, right, we want you to sniff the packets that are going through between the setups. Okay, so some of you might think, oh, wow, this is way beyond what we can actually do in terms of deliverables and our knowledge. The answer is it's an extension. And why do I say just as an extension? Only because man-in-the-middle attacks are very, very well studied, right? What do I mean by is very well studied? Is that there is a myriad of information available, right, for you to understand how man-in attacks can be simulated and so on and so forth. Okay, so this project has taken on more of an applied nature than a theoretical nature. Which means, right, if you decide to take a look how I broke this down, I want you to accomplish two things, okay? The first thing is I want you to do a simulation of man-in-the-middle attacks. And in fact, I go on and then say that is that you do not have any restriction in what you can use in terms of how you want to set this up, which means you're free to use any open source, open access tools, packages, frameworks, any of that sort. It doesn't really matter what you use, as long as you are using them, right, without violating any copyright rules, which means obviously open source or open access. Okay, and I can tell you that these material exist, but your goal obviously is to source them out. Okay, then what do you need to do? Man-in-the-middle attacks, right, in general, right, because this is not a security course, it says this. Let's assume who actually gains access to a network at sort of a public network. Anybody here like has gone on to sort of gain access to internet, using sort of the service provider at sort of a cafe like Starbucks or LANs or anything like that? Anybody here has?
Like Richmond Center Wi-Fi.
Right, exactly,
Yeah.
right, okay. So if you're not using your cellular data, right, and you're using sort of the public network, right, now, if you've ever administered a network yourself ever before, which is set up a Wi-Fi access point, you know that you can actually change the SID to anything that you want. So by default, they usually might be, depending on the manufacturer, it could be a Belkin, it could be a Linksys, right? They'll have some SID that you can actually reconfigure easily. And in fact, the thing with the SIDs is that you can call it anything. In fact, I could call it Starbucks if I really want to. Now, the question is this the man-in-the-middle attack says this: your devices naturally attach themselves, so what we call association, right, to an access point that gives you the highest signal-to-noise ratio. Okay, so what does that mean? It means this is that if I now say this, right, and I'm not going to use Richmond because it's too large of a place, but if I were to say this, okay, Chantel likes to go to a Starbucks in her neighborhood. Okay, and usually Starbucks likes to have sort of the first floor sort of front stores where obviously it's part of a building. Okay, which means we could have Bob that lives on top of this particular Starbucks that Chantel frequents. True. Now, Bob obviously, right, knows a lot about networking and data communications, right, and administers his own network at home, and he decides, so, you know what, I'm not going to attempt to steal information from the networks, right, of all of these public networks. So what is Bob going to do? He's going to say this, I'm going to buy an access point, right? I'm going to spend a couple $100s on it, right? Get this access point where, in fact, I can now configure it somewhat in a way that I can actually boost the power transmission within FCC limits, right? So that it is desirable for many of the end users to attach to my access point rather than, right, the access point provided by Starbucks. So what does that mean? Instead of going through Starbucks, it's actually going through Bob's access point. And obviously, Bob sits in the middle. That's why it's called the man-in-the-middle attack. So now everything that Chantel uses on Starbucks, including a banking and all that stuff, right? She may say, okay, I'm attaching to it. I'm doing WPA2 in terms of encryption. But little does she know, she's gaining access to the networks, right? Or the services that she's trying to, right? The web servers and so on, so on, through Bob's network. Where now, obviously, because Bob is an administrator of the network, now attempts, obviously, even though it's encrypted, has the ability now to decrypt the information, which means he or she, right, is now, well, Bob is a he, sorry. So Bob now, obviously, right, can see the data being transmitted. And obviously, what does Bob do with that? Well, he steals that information and then obviously, right, pretend to be Chantel, right, logging into all of Chantel's account, emptying all the bank accounts and whatnot, right? All this while Chantel assumes that her data is actually safe because she's encrypting it, right, through the use of WPA2. So that, in a nutshell, is what man-in-the-middle attack is, right? Sometimes we call it the evil twin. So if you've ever heard of the term evil twin, the unevil twin, right? The unevil twin, right? Obviously, but no, you know what, Chantel? You may have a student bank account only at this point in time, right? But obviously, right, as time progresses, right, the sky's the limit. And Bob is probably aware of that. And that's why, right, he's trying to gain access to information at a very early stage in your life. But in any case, right, the idea simply is very simple. I want you to simulate a man-in-the-middle attack. And there are different types of man-in-the-middle, like eavesdropping and information stealing and so on and so forth. Okay? Because I want you to be able to set up a network, right? And you can just simulate all of these data and their frameworks and stuff like that. You could actually get around doing this, right, with minimum coding if you choose to do so, right, or the least amount of scripting required, right, through the use of packages. But the idea of that you can actually piece together the components, right, to create a man-in-the-middle network, right. That's the key learning outcome I want you to get to. Okay, so what do you do as a deliverable? this is in lieu of your final exam, okay? And I've broken up the project into 2 parts, right? The first part, right, is obviously the demonstration, okay? So I'll tell you this, right? This is not something that most students will be able to accomplish or complete overnight. So do not wait till the day before it's due and then start working on this, right? I'm releasing this to you 4 weeks in advance because I want to give you more than ample time to deal and work on this problem. So the idea is that I want you to achieve the learning outcomes, which is obviously understanding networks, understand how networks work, right? And then obviously try to steal information, right, between the client and the server. So you could do things through HTTP, FTP, it doesn't really matter. You could just set up something, right, and say, okay, I'm going to do an FTP, right, transfer some data, I want to steal that data. Okay, so the first deliverable that you have, right, and that I detail here, I don't know if you guys can see it. Okay, and sort of to answer sort of Chantel's, right, there are no restrictions on what you can actually do, the languages, the frameworks, as long as you do not violate any copyright rules. What I do ask for you is that obviously that I want you obviously to include a citation, right? And this is the proper way to do things, is if you're using somebody else's work, you must provide that recognition for that. Okay, Chantel? She's probably working on a project right now. So, okay. So in terms of demonstration, right, what I want you to be able to do, right, is that everybody gets 10 minutes. And I've given you actually the schedule of your presentation time. So you see that your time box for 10 minutes and that's it. Okay. No more, no less. Okay. What do? In the 10 minutes that you are demonstrating in class on the last day of class, which means July 18th, right, in your time sort of groupings, you will demonstrate a man-in-the-middle attack, right, for 8 minutes. So no, you don't need to do presentation slides. I want to see a live demo, okay? What you need to do is that you will detail your setup, obviously, within the 8 minutes, and tell me the type of attack, or man-in-the-middle attack that you're trying to sort of obviously show and demonstrate. And then you'll do that, and you'll do that using screen share on Bongo. Right, so you have your setup ready to go, right, at the time grouping that you have, right, and you're spaced out 10 minutes apart. Failure to demonstrate it, obviously, right, just simply results in a 0 for this component. Okay, will you be graded, right? Obviously, 20 marks out of 25, right, is allocated, right, to you being able to successfully demonstrate to the full extent, right, as much as you can, right, what a man-in-the-middle attack is that what you're trying to demonstrate. Right, the additional 5 marks given obviously to the clarity, the organization, and how well you deliver your presentation. Okay, so it's 8 minutes, your time box, right? Time is very strict, right? Be ready to go at your time grouping. So what do I mean? If you're scheduled at 9 to 9:50, you should be ready, all of you, at 9 o'clock. Right, you shouldn't, have to take 3 minutes, because all I'm doing is I'm making you the host, and then you're going to screen share, right? And then you're going to go ahead and do your demonstration. Okay, your time box in demonstration to 8 minutes, and I'll time you because I want to leave 2 minutes, right, to just have a quick Q&A, right, if there are any questions, either from myself or from the audience. Okay, and then there obviously, right, you completed that demonstration. Now, in addition to doing the demonstration, I've split up the project into 2 components, equal weights. So half the weight goes to your demonstration and half the weight goes into your project report. Okay, and what is this project report? Obviously, right, you're only trying to show me a successful demonstration of your setup. What I want you to do, obviously, is complement that with a report, right, that is terse but yet insightful. Which terse just means that it should be, not too wordy. It should be condensed, right? So if you're sort of putting in, a 10-page report, it shouldn't just be 10 paragraphs repeating itself. I want insights. To me, right, what's important, obviously, are the insights that you gain out of doing this project. Okay, and what do I mean by that, right, is I'm going to look for you, right, in terms of how you set up your problem, including, obviously, the problem statements and some of the related works in the area as you read widely. Okay, I want you to detail, right, and illustrate your setup, right, including the type of MIMT. So this complements this. This should be, right, a report on what you're doing in terms of the demonstration. And as well, obviously, right, what are some of the insights you gained, right, from this man-in-the-middle attack project, right? And as well as what are the best practices to actually prevent such an attack. Okay, and obviously, right, depending on sort of the depth and progress that you make, that might be obviously in addition to the conclusion of this work that you've done, right, additional future work that you want to attempt, right, and future work is always a great thing. And of course, right, there's a section now here for your citations because I've allowed you, right, to use sort of any external frameworks or packages to attain this. So that accounts for the other half of your project, right? So you have a demonstration, okay, that is due at the last day of class, and then you have a project report, right, that is due along with it. Now, I recommend that you actually write your report as you implement your demonstration, so that you're not finishing the demonstration and then coming back to write the report, right? I recommend that you do side by side, okay? You have 4 weeks to do this, which is more than ample time. But I do want to alert you that this is not a project that you can easily accomplish, just in the night, which some of you tend to do so. Okay, so get it started early. Do the reading now. Spend 1 week on sort of the research. Spend 1.5 weeks on sort of getting the demo up, right? And then spend a couple of days to polish it, right? Along the way, please be writing your demo, your reports. Okay. Any questions on your deliverables? Sure. So I could do that, but my intent actually was that you actually read widely as part of the research to do this problem. Edward? So why don't I do this? I prefer, so because it's quite a substantial report, a project, right? This is in lieu of your final exam. Being able to learn things on your own is just as critical based on the foundations that you have. It's just as important as being told and taught, what you need to learn. Okay, so instead of sort of, let's just spend time describing to you what the minimal attack is, how do you set it up, right? I would like you to research that, but I'll be willing to spend time in class to take questions on it. How's that, Edward? So why don't we do this, right? Take some time this week, right, if you can, right, after you finish your assignment, do a broad learning of what man-in-the-middle attacks are. I've given you a quick description of what it is. It's just essentially the man-in-the-middle attack means that there's something in the middle stealing information. There is no restrictions or constraints on the report, Chantal. Other than that, it should be terse, right? And what I'm looking for is insights. So I don't want you to be regurgitating what I can read on sort of, any sort of search engine on MITM. What I'm looking for is the insights that you achieve when researching, implementing, right, and demoing man-in-the-middle attack. I'm looking for that unique proposition from your perspective. And that's what insights are, is that what have you achieved doing this project? Is that clear, Chantal? I'm not looking for paragraphs and paragraphs of text describing to me what man-in-the-middle attacks are. I'm looking for what it is from your perspective, right? And why you set up and choose to do this type of man-in-the-middle attack, right? And what are you trying to illustrate? And why does it happen? How can you mitigate around it, right? And so on and so forth. Is that clear, Chantal? Okay. So that's what it is. Now, in terms of deadline, okay, you see that there's 2 deadlines. In fact, one deadline is actually the Friday, and then the other deadline is actually the Saturday. So the Saturday, right, you'll be doing nothing but demonstrations. And then I'll be very clear. I don't want you to have to sit for 3 hours, right, which, what this is in fact, it's 4 hours, okay? I've broken up you into groups of 5, which means 50 minutes per grouping. You're only responsible to be present in your grouping. So, for example, right, Irana is grouped to the morning 5, right? She only has to be present between 9 to 9:50 or 10 o'clock, roughly. And then she has to obviously sit in everybody else's presentation, but she's not required to sit in between 10, 11, and 12 sessions. Okay, obviously I'll be present in all of them. But if you want to, Irana chooses to say, I always want to listen to sort of what Melody is doing. So she could come online at 11 o'clock and sort of, have some insights to what Melody is doing. Or maybe she wants to listen to what Bob is doing, right? So she could log in at 11 o'clock. But you're not required, but you're required minimally to be present in part of your group, as part of your grouping. So this is what I mean by, demonstrations are grouped, and you're only required to attend the demonstrations in your grouping. Okay? But the work is to be done prior. Okay, what I mean by that is that everything is actually due the afternoon before, which means Friday at 5:30. Okay, what does that mean? Okay, you should submit all the files you use for the demonstration, right? Including all the scripts, any source code, any frameworks, along with a detailed instruction on how to build and run your demonstration. So you should have everything done actually prior to Saturday morning. I don't want you to be working through the night. I want you to be done the day before, so that you're resting and polishing, how you deliver your presentation the day after. Okay, so all of this, right, everything that you need to do, right, needs to obviously, right, be packaged into one zip file, right, that including the instructions on replicating a demonstration. Is that clear on what's expected here, right? So you submit all of that into your demonstration.zip, submit that. As well, obviously, you should have your report done as well, and you do that in a single report.pdf. And there are 2 folders I've already created, and this is all due the evening before your presentation. So all this is due Friday at 5:30. I should be able to take this folder, replicate your demonstration, right? Because the instructions are provided. Okay, you can use any plugin. You can run this on Mac. You can run this on Linux. You can run this on PCs. Okay, as well as the final report. And all you have left to do on Saturday, which is the last day of class, is to log in before your grouping time, and then you have a 10-minute presentation while watching 4 others. Any questions on the project? And sort of what the expectations are from you in terms of this project? Anyone? No. So if you're running off a virtual machine, obviously, right, you will have to obviously tell me that you're running off a virtual machine. You need to sort of tell me the platform that you have as part of your virtual machine. Okay, Ellen? Are you running off your own virtual machine, or are you running off BCIT's virtual machine? Like, are you trying to use VMware off an instance on the BCIT network? Or are you running off a virtual machine locally? Oh, I see. Okay, that's fine. Okay, so you just have to tell me that's a virtual machine, right? And then obviously, right, you need to tell me how to set it up in this, because I have access to virtual machines as well, so I should be able to replicate that. Okay, Alan? Okay, any other questions on the project? Okay, as I said, start this week. Plan out the time for you to complete this. This is not a project that you can produce a good result, right, in overnight, right? So I want you to start this as early as possible. Okay, and the important thing is to have fun with this, right? Is that once you can set this up, right, then you have now illustrated, right, in fact, how, right, to at least, right, on a controlled network, right, how to actually steal information. And I'm not advocating that you do that, but from an academic approach perspective, right, that is a good exercise for you to actually try to do that. And obviously, right, the question is now, as part of the report, right, is how do you, right, mitigate against man-in-the-middle attacks? Okay. So that's your course project. This will be in lieu of a final exam. Okay. As I said, right, there are 3 more deliverables for you, right? Your assignment 3, which is due this coming Wednesday. There'll be a assignment 4 that is due that will cover the material through the end of the class, right? And then obviously at the last day of class, in lieu of a final exam, right, you're going to demo this project along with all the deliverables the day before.
So just to
Yes.
confirm, it's okay to use open source tools to demonstrate that?
Yes. Yes.
So if that was the case, so do I just provide a link for the use tool or something like that, or whatever?
No, because there's so many tools.
Yeah.
So there are many tools, and I want you to piece it together, because you could illustrate some of the stuff. Say, for example, using Wireshark, right? You could choose to do an HTTP. You could choose to do an FTP. I want it to be unconstrained. Otherwise, I want you to actually find these things. So part of your research is understanding enough what needs to be done, instead of me giving you an entire list. Do this. Well, then that defeats the purpose of the project.
Yeah, but my question, if it's an online tool, so I just provide you with what exactly?
Yeah, exactly. Tell me, oh, you're using Wireshark, for example.
And okay.
Right, exactly. Like one piece is a Wireshark, right? How are you setting up your server? Are you doing a telnet demo? Are you doing an HTTP demo? Are you doing an FTP demo, right? And you might want to contrast that. Oh, what if somebody uses HTTPS?
Okay.
Right? And stuff like this. I want you to come up and create this. So it's open-ended on purpose. But the deliverable is very focused. You have to demo a man-in-the-middle attack. But the application, right? Whether somebody's doing an FTP or HTTP, a telnet session, it doesn't really matter. The illustration of how you do it doesn't really matter. But it has to be a live demo.
Okay.
Does that make sense? Of your own sort of setup, where all you have to do is that you will demo it to the class, right, using screen share on Bongo, just like what I do now. Does that make
Sounds
sense?
good. Yeah.
Okay. It's open-ended, but with a very specific deliverable. And the reason for that is because I want all of you to look out and look into this on your own, so that you're not all coming up with the same solution. Obviously, right? Is that clear?
Makes sense. Yeah.
Okay, so read this again, right? And please, okay, as I said, my purpose here is not to give you the instructions how to do this, but I want to guide you down to do this. And the work that I want you to do is on your own research and your own setups and so on and so forth. So it will take a bit of a substantial amount of time if this is very new to you, but 4 weeks is more than adequate. I can very clearly state that to you.
It's almost 3 weeks now. Yeah.
Right, 3 full weeks to get that. But I did release this on a Monday or something like that, right? So but I, again, as I said, because I only meet you once a week, right? We seem to only see each other every 7 days, right? Which means that we're losing, every time I see you is actually another 7 days.
Yep.
Okay, so please get on with it, right? I'm here to support you either on email, on class, right? But you should try to attempt to deliver this, okay? Okay, so let's take a 10-minute break here. Okay, a formal break. Okay, 10 minutes, right? We'll resume right at 11:20, right, and then we'll get on with error coding and detection. Okay. Okay, let's get Okay, so let's sort of get started. Is everybody back?
Yes.
Let's save this. Okay, so I want to get onto something really fun, actually, in terms of coding theory. This is not new, actually, for you guys, because you've actually been exposed to something known as parity codes. Okay. Oh, I should share the stack of slides here too. So why do we have to do error detection and correction here in sort of datacom? Why? Does anybody know why? Why can we not get away without having to do some kind of error detection?
Because whatever medium you use, it will definitely be subject to some sort of noise or impairment or something like that.
Exactly. Okay. So the error detection is real, right? And it's real because obviously, right, the channels are always assumed impaired. Okay. So we could get away and say, you know what, let's not do this, right? Why spend time doing error detection? Why spend time doing error correction? Just transmit the bits as is. Now, the end user today, right, that we are all part of, right, always assumes, in fact, that the data that you receive is actually accurate. Isn't that true? I mean, have you ever really wondered, right? Every email that you get from me, and I say, okay, well, you know what? There's a project, and the project's due July 18th. Have you ever questioned whether or not, in fact, that there was any errors with that transmission?
No.
Maybe I intended to be July 16th, but somehow there was an error and you received it and it was July 18th, right? I mean, when Albert gives you a mark for C, your grade for C, right? If he gives you, 95%, would you ever question that? What if he gives you 45%? Would you question that?
I'll question both if it seems abnormal.
Right. But if it's within range, I mean, maybe you really got, 93 and he wrote 95 for you. So I don't know if you guys are aware how marks are entered on BCIT. I mean, it's individual students, one mark at a time, and we type it in, usually at midnight. But in any case, right, the assumption by the end user, right, is that unless you receive something that is obviously completely questionable, you're very unlikely going to question the integrity of the data you receive otherwise. Okay, and we as a network have the responsibility of ensuring that the data, in fact, that the receiver receives is what the sender intended to. Okay, and this is why we do error detection and correction. So I'm going to go through sort of the basis of why and how we do error detection. But more importantly, we'll end up with two techniques, right? One is called CRCs and one's called checksums, two very widely used techniques for error detection. And those are the two questions 2 and 3 on your assignment 3. Okay, so we'll look into the class of what is known as block codes. Okay, and obviously, right, this class of block codes have different types of codes in it. Like, I'll give you the structure of it, how redundancy sort of helps achieve, error detection, right? And obviously, how do we find ways of doing it? So I'll give you an example, right, to sort of just to motivate. Okay, assume I know that I operate in a very, very noisy environment. Right, because obviously we have Bob in the class, and he's always eating, chatting, doing whatnot to disturb the class. Okay, one way I could get around it, right, is by saying this. You know what? Everything that I teach, I'm going to repeat it twice. Everything that I teach, I'm going to repeat it twice. Today we'll look at the introduction, the block codes, and the cyclic codes. Today we'll look at the introduction, the block codes, and the cyclic codes. So if I do everything twice, right? And I could say, you know what? Instead of doing twice, I could do it 10 times. At some point, right? You as the receiver will receive at least 1 out of the 10 copies of the same information. True? So that's a very easy way of getting around errors. If I know that the channel that I'm in is very noisy, I could start to repeat. 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 At some point, right, regardless of what the environment is, there is a high probability that you at least receive one of those repeated transmissions. And we could have circumvented the problem as such, but why don't we do that? I mean, Chantal says, please don't do that, right? But why not? I mean, we've always learned,
lots of redundancy, wasted time, wasted resources.
That's right. Okay, but in exactly the cost, right? But in academia, though, repetition is deemed as a good thing, right? The reason why I review truly, right, the entire sort of classroom lecture in a abbreviated way from the previous lecture, right, is because that actually provides redundancy and opportunity for you to ask questions. Okay, so the question then is this: is that obviously, right, we need to find ways to provide some additional information without repeating the entire content again and again and again. Okay, and the reason why we do that, right, and how we do that, right, depends on the type of coding that we're actually going to use. Okay, so we're trying to do this, right? Okay, I know that in order for me, right, to be able to detect errors, I need to have additional information, which means receiving just an error message is not going to give me enough information to correct it. But short of repeating it myself over and over and over again, and I haven't defined, you know, how many times of repetition I'm going to do, but at least I need to give you some additional information. And the question now is this: what are these additional information? And how much of this additional information, right, do I need to provide you with, so that you can have with a level of high probability, at least be able to detect the error, and if possible, attempt to try to correct it. Okay, so what do I have, right? I mean, the idea behind error detection, right, is that we know that obviously that the physical channel that we transmitted, right, has interference. Okay, it is noisy, it is impaired. What that means, obviously, is that, remember we talked about distortion, we talked about attenuation. Those are all the impairments that we can introduce into the system. But obviously, the number of bits that are affected, right, is a function of the data rate and obviously the duration of the noise. Which means if all Bob does is he makes a little squeak once every hour, right, that likely has very little impact on the bit errors, you know, that will happen throughout this entire class. But if Bob goes ahead and makes a squeak every second, so effectively, right, he's going to be squeaking through the entire class, I believe, obviously, that's now going to get a noticeable impact in your ability to absorb the lecture. And so if Bob has a tendency to do that, then my goal, obviously, is to ensure that I do something to mitigate that. Okay, either I mute him, right, which means effectively I'm increasing the signal to noise ratio, right? Or then I have to do some repetition of some form or some redundant information, so that at the end of the day, right, you get the intended message that I have intended to send out. Okay, so in practice, right, what we see is this: is that there are notions of single bit errors and there are notions of burst errors. No, I don't. Thank you, Bob. There's no need for you to squeak every second here in class. Okay. The question now is this: is that what do you think is more common, single bit errors or burst errors?
Burst errors.
Burst errors. Why? Why, Rana? You're absolutely right.
Because normally the data rate is high and the noise would definitely go for more than 1 second or something like that, which means it would definitely affect multiple bits.
Exactly. Okay. The reason why we are more in a situation where there are burst errors, which means multiple bits being affected, and note this though, right? A burst error doesn't mean that every bit in that burst is in error. In this case, right, only some of the bits in that duration is in error, but it impacts more than one bit, right? And the reason, the fundamental reason for that, right, is obviously because of the high data rates that we transmit. Remember, we're transmitting minimally roughly at 1 billion bits per second now. 1 billion bits per second. So even if Bob makes a squeak of some kind, that is unlikely to impact only one single bit, but multiple bits, right, in a duration of time that he produces that squeak. Okay, so burst errors are obviously more likely, right? If we take into context, right, that there is a error or a noise, right, that it's happening just 1/100th per second, like, you know, Bob does this little squeal, right, whenever he does that. Okay, even at a kilobits per second, right, I'm going to impact at least 10 bits. Now, at a more nominal 1 megabits per second, right, which is considered low data rates, right, in today's terms, right, that's already 10,000 bits. At 1 gigabits per second, that one little squeak that Bob does can impact 10 million bits. And obviously, right, as I said, the problems that we face today only continues to compound simply because our data rates continues to go up. The reason our data rates continue to go up because you guys are consuming more and more data. Does that make sense? Okay, which means this obviously becomes a bigger problem as time progresses, and because it becomes a bigger problem, then we have to find ways, obviously, to mitigate it. Okay, and muting Bob, right, is not a solution, because obviously he has every right to speak within the class, right, in whichever language he chooses to do so. Okay, so how do we stop, right, as a general, or how do we, what do we do as a mechanism in general, right, to try to detect these errors? As I said, right, the easiest form of error detection is by repetition. And there is truly a code known as repetition code. I could say the same thing 3 times in a row, 4 times in a row, 5 times in a row. Depending on the severity and the duration of that noise, right, obviously, I now have to adjust my repetition. But the idea is this, is that we know that it becomes inefficient, as most of you have said, not just in time, but it's extremely efficient. If remember, right, if all I do in the entire class is to say one word because of the high level of noise in the channel, right, that is not efficient use of the channel at all. So then the goal is this, okay, if I have a certain number of bits I want to transmit, how much more redundant information should I provide you with without repeating myself? And then the next more important and more difficult question really is, what should the redundant information be? Supposedly I say a sentence. Today is a very sunny day. Right? What do you think is the most critical words within this statement? I mean, what is the bulk, what is the core of the information I'm trying to convey? Perhaps the word sunny. Right? Today is the weather, exactly, right? I could say sunny day, right? So if I simply say to you, sunny day, right, you probably get the equivalence in terms of information as the whole statement, today is a very sunny day. Right? But if I only repeat the words is you probably get nothing out of that. Right? So it's not just about redundancy. As I said, we don't want to go and repeat ourselves completely. We want to provide the minimum amount of redundant bits because every bit counts, right? Redundant information means bits you otherwise should not have to send. In addition, though, right, I think the more important question is, what should these redundant bits be? Okay, say I'm transmitting you some numbers, right? The numbers 1, 2, and 3. And I want to send you some redundant information. What should I send you as some redundant information for you to detect errors? I'd be short of repeating myself 1, 2, and 3, right? Perhaps 1, 2, and 3, right? Should I, if I want to sort of reduce the amount of redundant information, should I transmit you 1, 2, or 3? None of which really helps you detect errors, true? I mean,
I
you
guess
know that
in the weather example, you can add the date of today to kind of like specifically saying that
Sure.
it is today.
Right, exactly. Right. Yeah. But what about numbers? So I just give another example, right, which is 1, 2, and 3, right? So it's a little less subjective. How do I let you check with the least amount of information whether or not you had an error in your receiving of the data? Right? Repeating 1 is probably not very useful. Repeating 2 is not very useful. Repeating 3 is not very useful. But what if I sent you the value 6, which is the sum of the values? Would that help you detect errors?
It kind of would. It would
exactly
limit the scope of, you know.
Exactly. So it's not 100% like Rana said, right? Obviously, right? Why? Because if I say this, right? Okay, I'm going to send you, right, the numbers 1, 2, and 3, right? Which I know adds up to 6. Then I said, okay, I'm going to send you one redundant piece of information, which is 1, 2, 3, and 6. So your way that Bob receives this information is going to add up 1, 2, and 3. Oh, it has a 6 grade. You know what? There are no errors. But bear in mind, though, right? There are many other ways of getting to 6. I could have intended, right, to send you 2, 2, and 2. But you receive 1, 2, and 3. But they all, in both cases, also add up to 6. So it's not a complete solution, right? It's not foolproof, but it's better than just me blindly sending to Bob, right, the values 1, 2, and 3 and asking him, did you receive an error? Now, what reference is he going to do to determine that? Right? There's no context, right? So what I'm trying to drive at is this, is that we're trying to send information, and we know that, right, the central concept and how we actually do that, right, is through some redundancy. But in redundancy, we want to be very careful with the amount of sort of bits that we send as redundant bits. And we also want to be very selective, right, in the type of information that we're using as redundant information, right? Both of which, right, are two important considerations, right, in how we create all the types of different codes that we actually have. Okay, and then the last point I want to make as an introduction is, okay, why do we do detection and not correction? Because correction is computationally very expensive. Okay, just giving an example, right? If I want to try to find 10-bit errors, right, out of 1,000 bits, it is probably easy for me to detect that, oh, you know what, this 1,000 bits, if I add up all these values, are not the same as the sum, I have an error. Now, but it's a very different problem now if I say this, okay, I know that there's an error and I want you to correct the error, which means you have to find out where these 10-bit errors are precisely within a stream of 1,000 bits, which means all permutations of where these 10 bits can be within 1,000 bits. That is a very difficult problem because that is a 10 to the 21. Right, in terms of the number of permutations, right? So we really are doing 1,000 choose 10, right? In terms of how many different possibilities, right, in that 1,000 bits that you transmit, right, where these 10 bits can be, these 10 bits are in terms of errors. Okay, so what is coding? Coding simply says this. Let's add some redundant information, and we're going to go through different techniques of doing that, right? And when we do that, right, there is a relationship, right, of creating these redundant bits. So in this case, right, the previous example I gave you is, oh, you know what? The redundant information is just the sum of the values. In fact, that's checksum. That is as simple as what checksum really is. If I send you some values, I'm going to send you as redundant information the sum of the values. And then the receiver knows that. So Bob gets the values 1, 2, 3, and 6. He goes, okay, add 1, 2, and 3, right? If Bob can add correctly, he should get to 6. Which obviously, right, will match up, right, with the sum. Okay? The thing that we want to be obviously most concerned about, right, is what we call the code rate, right? And the code rate, obviously, right, is K over N. We'll talk about that very quickly. The number of used bits over the number of transmitted bits. Which means, if I say this, right, I'm going to send you 1, 2, 3, and 6, right? If I consider each of these values in a single bit stream, right, as a common denominator, then my code rate is 3/4 because I've only sent 3 useful values, but I'm sending you 4 values in total, right? Which means I want to get as close as possible to a high code rate. Okay, if I do a 2 times repetition code, my code rate is 1/2 because everything that I transmit is double of what the information actually is. Okay. So what is block codes? And I'm going to use the whiteboard, right, to sort of illustrate to you what the block code is all about. Okay, from a definition point of view. Okay, so supposedly, right, I have some information I want to send you. Okay, and the idea behind this is that, okay, I take this message and I'm going to break them up into chunks of information, equal components of it. And each of these will contain k bits, and k bits, and so on and so forth. Okay, but obviously, right, I cannot transmit k bits because I want to set some redundancy to it. So mathematically, I'm going to say this. Okay, these components of k bits, I call them data words. the data, right? Because it's data. Okay, so it's a data word. But I'm going to transmit, right, a not n number of bits, which is actually k plus r. So k is a data word, n is actually the code word. This is the code word is what I transmit, and r, right, is the redundant bits. And the question that we have in all our scheme is, what is this r? Right? If we specify mathematically as such, then the code rate is going to be k over n. Because this is the number of useful bits in terms of information. This is the total number of bits I transmit with the addition of the number of r bits. Okay, so then the premise of sort of code rate is this, is that, okay, I know I have k bits in data words, and then I have n bits, right, in my code word. We want n to be much, much larger than k. What does that mean? And why? Because if you get this concept, then coding becomes very simple to you. Everything else just becomes a simple technique. Okay? If I look into the code space, right, and I say, okay, it's a 4-bit code, then I have an n space, right, which is obviously the superset of n, right, which means if the data word was 1, that's 4 bits, right, so it goes from 0, 0, 0, 0 to 1, 1, 1, 1. And now I'm saying that I want to represent all of these codes, right, in 20 bits. So I'm going to try to transform all of these 16 into, obviously, 20-bit codes. Right? Where does everybody see that the bit differences between, and you might have heard of something known as Hamming distance. Does everybody see that the Hamming distance between the codes here is at most 4? For a 4-bit code? Because, I mean, in an extreme case, right, it's 0, 0, 0, 0 versus 1, 1, 1, 1. There are 4-bit differences, right? So Hamming distance, or if you recall from 27.1, is just number of bit differences within a code, between 2 codes. What that means, right, is this. If I expand this into a 20-bit code, and I'm mapping 1 to 1, have I increased the Hamming distance, or have I not increased Hamming distance between the 2 codes? Does everybody follow what I'm saying? Increased it, exactly, right? So the worst case, right, if I say this is going to map now into 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, so up to 20 bits, and the next one is going to be 20 ones. The Hamming distance here is 4. The Hamming distance here is 20. The more bit differences, the more distinct they are. Okay, so we really want n to be really large. Is really what the motivation is. Okay, to give another perspective of how we look at this space here, right, on how we increase. Remember, right, n is k plus r, which means I really want n to approach infinity because I want to increase the Hamming distances between the codes. But on the other hand, I have a constraint, because if I increase n to infinity, which means I have r goes to infinity, then k over n goes down to 0. Is that a good thing or a bad thing? Obviously, right? I don't want code rates of 0 or approaching 0, because I want as high a code rate as possible. I don't want to use a zillion bits to represent half a bit of information. Okay, so these are the 2 constraints. On one hand, and having 2 constraints, is opposing constraints, is always a good thing. You want, on one hand, this to be as high as possible, right? But on the other hand, you also want this to be as high as possible, which means you need to constrain this guy and bring it down. So this opposing, right, is where you find the optimal value somewhere in between. Is that clear? Okay, so now if we have this, right, and we know that we have 2 opposing sort of functions, right, then we know that we have a code space of 2 to the n versus 2 to the k. So we increase the Hamming distances. Okay, so what do we do now? Very simply, it just simply says this. Okay, if I have k bits of data word, I'm going to generate a code word out of it. Okay, a generation of code word means that I'm going to go through some mathematical function and then create n bits out of the way, which really is defining what the R bits are, the redundant bits. I transmit through this a unreliable transmission, and the receiver, right, if it does the same reverse of the generation, I should be able to take this n code bits, which I assume is impaired because it's through an unreliable function transmission medium. If it checks out to be okay, I'm going to extract it because no error detected. If it does not check out to be okay, then I'm going to discard it. Okay, but there's the conditions that needs to be met. Okay, and the first is this: is that both the sender and receiver have a list of valid code words. True. If I'm going to transmit some information to Melody, and I'm going to tell her, right, I'm going to now give you a list of names, right, out of the dictionary. Okay, so every word that Melody receives, right, she's going to check against the dictionary. Oh, the valid, the valid, the valid, the valid. Okay, but the more important thing is this: is that, and we call that in coding theory the dictionary, right? So it's the same thing. But the more important thing is that, is it possible for an original code word to change into another valid code word?
Yes.
Yes, exactly. Because what I mean by this is if you go back to the example that I showed you earlier, right? If I show you this example, and the one here, oh, not here, one here, okay. If I say that the code words are 0, 0, 0, 0, all the way to 1, 1, 1, 1. Now let's assume, right, there are 16 codes, right, because there are 16 counts of these values. But is it possible that this code, which is valid, had an impact on the last bit and became received as this? Is it possible? 1 bit error, and it caused this value to be received?
Which is also a valid word code.
Which is also another valid code word. Okay, so I need to guard against this. And the way I can do this, right, is try to increase the Hamming distance so that no 1-bit errors results in another valid code. Because the more bit differences there are between the valid codes, the more difficult it is for one valid code to be transformed into another. So in this extreme case, right, all bits have to get impacted before it becomes another valid code. Does everybody see what I'm trying to do? Whereas in this case, only 4 bits needs to get impacted. Because this could be received by the receiver, right? If Melody sends this to Bob, Bob gets this, and Bob is like, okay, Melody told me 1. Because how is he going to know that, in fact, that this is not a valid code? He cannot know exactly. He will take blindly whatever mark, right, that Albert assigns him for his C course, right? Whether it's 65, it's 25, or it's 95, right? He will gladly take whatever Albert deems, right, he has achieved in terms of the grade for the learning outcomes he has achieved. Okay, because he does not know. Okay, so if we go back to this structure, right, it is very important. Not only do you know the list of valid codes, but you also need to know whether or not actually the actual valid, the original code word, right, has in fact changed to an invalid one. Because if it changed into another valid one, then it becomes an undetected error. Okay, any questions on that? And then I'll give you an example of what coding is really all about. Okay, any questions? Any questions? Okay, so very quickly, right, let's take a look at this. Let's assume my data word is of length 2, right, as shown in this case, and my code word is of length 3. Okay, and this is the dictionary. So I said, if you intend to send 0001, 1011, these are the codes you transmit. 000, 011, 1010. So it's a 1-to-1 map. Okay, so someone wants to send 01. Okay, so Melody goes, okay, I want to transmit 01 to Bob. Okay, so she looks up the dictionary and says, the dictionary says, okay, to transmit 01 to Bob, I need to transmit 011. Well, then Bob receives 011, looks at the dictionary, yep, it exists. Okay, valid code. What she intended to send me from the data word, right, is actually 01. I'm going to extract 01 from it. The second scenario is as Melody sent out 011, it was impaired on the first bit, on the MSB position. Well, Bob receives 111, and he goes, okay, let me go to my dictionary. Within my valid codes that I should get, there's no 111. I know right away that, in fact, some error occurred in the transmission because this is not a valid code word. So it says that, okay, Albert cannot give me a grade of -5. Right, Bob? If he did accidentally input -5 for your C course, right, you know something went wrong. Okay, because obviously, right, the minus sign is right, 2 keystrokes before 9, right? So he might have wanted to assign you something. Like, you don't know what he wanted. It could be 05, it could be 95, it could be 85, right? But in any case, right, because it's not a valid code, you discard it. But obviously, as we said, right, some of the codes could be undetected, which means even though Melody sent out 011, you encountered a 2-bit error, and you received 000. Go to the dictionary. Oh, 000 does exist, and by no fault of your own, right, Bob? You decided, okay, I'm going to now extract the word 00, because that's what the dictionary tells me. If I receive 000, I'm going to extract 00, and if I extract 00, which is the right thing to do, but unfortunately, you conveyed the wrong information. Does everybody understand the illustration that I've just gone through on what we mean by coding? So there's some redundant information that we need to put in. The redundant information helps to increase the Hamming distance between the codes, right? But there are a couple of conditions that we need to meet. Is that we both know what the valid code words are, and obviously, right, that the code word to be detected as an error became an invalid code. Because if it did not become a invalid code and became another valid code, then obviously this is what Bob is going to do. Right, because 000 is also a valid code word, and therefore he correctly extracted the incorrect data word. Okay, Bob? So why do I sort of know that it's an incorrect word? From a computer perspective, right, my goal is to actually compute the Hamming distance, because at the end of the day, right, so if you recall Hamming distance from 2721 that Jason taught you, right, the important thing is this, is that there is no difference between the receive and the transmit code. So I want the two codes to actually have 0 Hamming distance. Because they have zero Hamming distance, they're the same code, which means what's being transmitted, which is TOC, is exactly what is being received, which is RC. But there is another sort of notion, right? And we call that the minimum Hamming distance, an extension to the Hamming distance. Okay. Now, the minimum Hamming distance, right, is a value that you can obtain by finding all of the Hamming distances between all possible sets of code and picking the one that is the smallest, which means you're trying to figure out what is the minimum amount of differences between the two code words that can be transmitted. Why is this important? Why do I care about the minimum Hamming distance? Anyone? Why do I care about the minimum Hamming distance?
Indicate the range of valid code word that you can send.
So with a large, not the range though, but
Okay.
with a large minimum Hamming distance, is a large Hamming distance desired or a small Hamming distance, minimum Hamming distance desired? Do you want the code to have a very large minimum Hamming distance, or do you want the code to have a very small?
Well, not too small, I would say. Like,
right. So you want it to be large. Period.
Yeah.
Okay.
Was...
Let me give you an example. And Bob, I'm going to use an example. Okay.
Okay, sure.
Okay. So Bob, and I'm making this up. Okay. I have no idea about Bob. I actually don't even know Bob. I don't remember what he looks like anymore. Actually. Okay. Actually, maybe I do, because I know every time I look at Brett, I think of Bob. So the question that I have now is this. Let's assume Bob, right, I'm making this up, has 10 identical twins.
Okay.
Okay, he has like 9 other siblings that are all identical twins, right? Somewhat identical, right? Because obviously we know that twins so I don't know what that's called, a dectuplet or something like that. Okay, like a dectuplet, right? So he's got 9 siblings, right, that were born at the same time, that were sort of looks very much like him.
Okay.
Okay, let's assume that. I want the minimum Hamming distance to be large between all the bobs, right? All the 10 bobs, true?
Yes.
Because if I have a very small Hamming distance between them, then it's difficult for me to tell them apart. So I'll give an example, right? If all the siblings, right, have slight differences, okay, some of them drastically different, some of them minimally different, and the 2 bobs that look most similar to each other, right, only has one very subtle difference, which is obviously, right, one eyebrow pointing up and one eyebrow pointing down, minimally. Does everybody see that? If I want to successfully differentiate between the dectuplets, all 10 bobs, the constraint for me to be able to successfully tell them apart is most constrained by the 2 bobs that look most alike. Because I'll very likely be able to say this, oh, obviously, right, I can tell between Bob and Bob 1 because they have very distinct differences. I can tell between Bob 1 and Bob 3 because they're very distinct differences. But between Bob 1 and Bob 10, right, the only difference that they have, right, is that one of the eyebrows point up and one of the eyebrows point slightly down. Which means if I look at the entire code, the ability for me to tell apart all the codes within this dictionary is very much constrained by the 2 codes that are the most similar. So this is where the minimum Hamming distance comes into play, right? Is that in order for me to tell apart between 2 individuals or 2 codes, right? The constraint is the 2 codes that look most alike each other in the dictionary. Because everything else is simple, with the exception of the one of the 2 code that looks most similar to each other. Okay, and this is how we're going to apply sort of the minimum Hamming distance. Now, if we know the minimum Hamming distance, which we'll denote here as dmin, then we know that the error detection capabilities, which we'll denote as S, to be dmin minus 1, which means I can always detect errors, guaranteed, up to dmin minus 1. Okay, so to recap, right, Hamming distance, and I'm going through this quickly because these are things that you've been exposed to already in 2721. Okay, Hamming distance between 0, 0, 0 and 0, 1, 1?
2.
2. Hamming distance between 1, 0, 1, 0, 1 and 1, 1, 1, 1, 0. This should be quite quick, right? You're visually scanning through and seeing how many bits are different in their positions. How many?
3.
Yeah. Okay. What is dmin of this? How do you determine the dmin?
First and second is 2.
Mm-hmm. Exactly. So
Second and third is 2. Also, I'm guessing the last pair is 2 as well.
exactly. So you have to go through pairwise, right, between the codes in the dictionary. So this is the dictionary. There are 4 codes in this dictionary. You're trying to figure out all the bit differences between pairs of codes. And the dmin, right, is the minimum of the differences between different pairs of codes. And which in this case, right, because they're all 2, the dmin is 2, 2. Now, if you know dmin, right, if I tell a code has dmin of 4, which means the 2 closest code that looks that have the minimum number of difference between them
As 4
right,
changes.
Is 4 changes, then the maximum number of error detection I can do, right, is dmin minus 1, which gives me I can detect up to 3-bit errors. Guaranteed. Doesn't mean that's all I can do, but that's at least what I can do. Okay. There is another class, right, an extension of block code. So this whole area of k plus n, right, k plus r equals n bits, right, is what we call block codes. There's one simple extension of block codes called linear block codes. And in fact, all of the codes that we're going to look at are called linear block codes. Okay. And the reason why we look at linear block codes is because they have a very simple property that we can actually use. Is that we can determine the error detection capabilities of linear block codes very easily. Okay, but first of all, what's a linear block code? A linear block code simply says this, right? Is that, in fact, if you take the exclusive OR between any two code words, and that also produces another valid code. So for example, if I have a dictionary 00001110110, da da da. If I take the exclusive OR between any, so 0 and, you don't have to take the 0 code with anything because it will always produce the other thing. But if I take 011 and 101, it produces 110, that's the other code. If I take 011 and I do it with 110, that produces 101, which is the other code, right? And so on and so forth. If the exclusive OR between any valid two code words produces another code word, then this is a linear block code. Now, does everybody see that when you take the exclusive OR between two codes, it's the same operation as how you would find the Hamming distance? Does everybody see that? In fact, this exclusive OR operation, right, 011 exclusive OR 101, tells me that they're different in positions 2, 1, and similar in position 0. Does everybody see that? It's telling me the first two bits from the MSB position are different, and the last bit is the same. If I take these two together, right, it's telling me the first and the last bit are different. Right? Does everybody follow?
Yes.
Where there's a 1. So really, this value I get here, while it produces another valid code, is also the Hamming distance. Does everybody see that? It's actually also the Hamming distance. Which means if I have a linear block code, which means the exclusive OR operation between any two valid codes also produces another valid code, then the dmin, which is the minimum Hamming distance for the entire dictionary of this code, is simply the code with the least number of ones, with the exception of the all 0 code here. So I don't care about this first code, right? So all of them have at least 2 ones. So they're all equal. Then dmin, right, is simply just a number of ones, which is 2. Because all the Hamming distance is 2. And therefore, the dmin is actually 2. Now, there's going to have some very useful applications of it because we can now very easily determine, remember, we're trying to do error detection, right? And if there's an easy way to find out the error detection capabilities of a code, right, we're more than halfway through the problem. Okay, so what do I mean? Parity codes. You guys have seen this, right? Parity codes. Right? What does it mean? Okay, well, I have some data words, right? And there's 16 of those because I'm using 4-bit data words, 0, 0, 0, all the way through to 1, 1, 1. I'm going to represent this as a code word with 1 additional bit. And I'm going to now look at them all as even parity codes, which means the transmitted code word all have even number of 1s. Do you guys remember this? Parity codes, even parity codes. So regardless, if there was a 0, 0, 0, I'm going to insert a 0. So the last bit is your parity bit. Okay, but I'm going to take this out so that it doesn't sort of obscure your screen here. If there's only 1, 1, I'm going to add another 1, make it even once. If there's 1, 1, I'm going to add another 1. If there's already 2 1s, I'm going to add a 0, which means the codes that I transmit will always have an even number of 1s, which in this case will be either 2 or 4. And I'm using the last bit, which is what I add, right, to actually create the code word. Now, this is also a linear block code. So then very quickly, right, then I can say this, okay, Rana, can you tell me, if you know that this is a linear block code, so look, focus on the stuff in blue. What is the...
Yes, always 2. Always the amount of change results in another code word.
Exactly, that's a linear block code. So then what is the error detection capabilities of this code word? How many bits is it guaranteed to detect in terms of bit errors? Remember, the ability to detect errors is based on the dmin, right? You care about the constraint on the codes. It's not the 2 codes that looks the most different, but the constraint on detecting errors is the 2 valid code words that looks the same, or the most identical, most similar.
And those could be, well, the amount of change is 2. Min is 2.
2, yeah.
Exactly.
Because
and therefore,
Oh, sorry.
1.
Go ahead. 1, exactly. Right? Because visually, I can scan down these code words now, and based on this definition of LBCs, right, I can easily find the daemon, because the daemon, right, is defined as the number of ones in the non-zero valid code word. So I go on and say, okay, without the exception of this, which of these codes have the least number of ones? And the multiple of those with the least, which is 2. And if it's 2, right, the daemon is 2 minus 1 is guaranteed to detect up to 1 bit. So if I give you an example on parity codes, right, and forget about the generation, this is really just here for you to sort of, you may have seen this, okay, but I'm not expecting you to be able to do this in terms of generation of sort of the even parity check codes, right, which really just is taking what we call modulo 2 arithmetic, right? If I have even number of ones that I'm adding up, and I'm only inserting 1 bit, I'm always going to insert a 0. If I have an odd number of ones, right, the summation of this will give me the parity bit, which is a 1. Right, and I'm going to add a 1 and mix this even parity. Okay, so the idea behind it is this: is assuming that I want to send the sender the data with 1011. Okay, and so now I know that I have to insert another bit here, which is the R0 bit, right? Which is what I can create based on this modulo 2 arithmetic. Okay, my goal is always to do this. If I take all of these bits that I receive, remember, right? So this is transmitted A1, A2, A3, A0. I'm doing modulo 2 arithmetic to create the parity bit, which is R0 here. But my assumption is that because this is unreliable, all the bits can be impacted, which means there's no guarantee that A0 through A3 will be correct. So I'm going to call them B0 to B3. In fact, the parity bit itself could also get impacted. So instead of calling R0, I'm going to call it Q0. Now, remember, right? I want even parity. If I want even parity, which means that if I add up all the ones, including the parity bit in modulo 2, I should get the value of 0. Right? Because there's an even number of ones. If I ever get a result of 1 by adding up all of these values, then I know it's not even parity, it is odd parity, and therefore I've detected an error. We call these computing the syndrome. Oops, sorry. The syndrome here. Okay, so if the syndrome is 0, there's no issues with the code, or no detectable issues with the code. If the syndrome is a non-zero, then we know that there was a detectable error that occurred. Right? To illustrate that, right, this example will show you sort of the values between it. I take the value and I want to set 1011. Okay. So instead of going up to a dictionary, right, that we did with our first example, I'm just saying this, right? This is a parity code. It's an even parity code, which means I can create the parity bit by adding up all of these in modulo 2. 3 ones will add up to be 1. The code that to be transmitted will be 10111. Okay, as before, if Melody transmits this, Bob receives this, he's going to add it all up. In modulo 2, this will sum to 0. Right? Because they're all even number ones. So your last bit, listening bit, will always be 0. If this is 0, syndrome is 0, right? Obviously, you extract the first 4 bits. And that's a data word. Now, what happens if this was a bit error? Now, let's assume after Melody transmits it, the channel impairs the 3rd bit, right? Or the middle bit, I should say. Okay. If this becomes a 0, then right away, what you have is the syndrome is not going to be 0. But the syndrome is going to be 1. And if the syndrome is 1, there's a detected error. And therefore, we do not extract the data word, because even with extracted, it's still a data word that is an error. What about if there's a single bit error change, but now in the parity bit? In fact, it doesn't really matter, because when in the transmission, we assume that any of these bits, regardless whether it's the actual data word or the parity bit that has been generated, they are equally probable to be impacted. And obviously, right, what we then take into account is that whether or not it's the data word or the parity bit, we always continue to compute the syndrome associated with it, which in this case, the syndrome is going to be 1. Now, obviously, I'm not trying to correct this, so I don't need to figure out which bit position was actually impacted. But you start to see the difficulty, right? Because I know that there was a bit error, but I do not know, right, as a receiver, where the bit error is. Okay? So what if there are 2-bit changes? Well, if there are 2-bit changes, this, in fact, depending on where the bit impact is, it impacted 2 ones. So this remain even parity. Now, if this remain even parity, the error, obviously, right, is not detected. If it's not detected, then obviously Bob is going to extract 0011, which obviously was incorrect because Melody intended to transmit 1011. But what if there were 3-bit errors? Let's assume they impacted 3 bits, right, where they all changed in values. Okay, then what happened? Well, if I do that, instead of 101 became a 010. Now it's no longer an even parity. I have a syndrome of 1. I know that there's something wrong with it because Melody told Bob that she's transmitting even parity. This is odd parity, and therefore I do not extract the data word. Okay.
Question if possible.
Yeah. So the point is this: is that even though, right, it is guaranteed to only detect up to 1-bit errors. In fact, parity bits can detect an odd number, right, of bit errors. Yes, Rana.
Actually, I was going to ask, if we know that even parity will detect up to 1 bit, why are we looking on errors of more than 1 bit? We know we cannot detect them.
Oh no, because we do not know how many bit errors will occur. But there's a limitation. What I'm trying to highlight is that because there's a limitation to even parity check codes.
Okay.
Because remember, right, my whole sort of premise was this, right, is that I'm going to now try to find the proper number of R bits and what these R bits are.
Okay.
And I'm highlighting based on use of parity bit where we're only inserting 1 bit, which is very minimal, right? I mean, to add only 1 bit to any string of bits we transmit is the minimum number of bits, true?
Yes.
It's the minimum you can transmit. But adding only 1 bit, and that's a very good question, is that it's trying to get to a point I'm going to try to highlight is that for more detection of errors, I need
more bits.
More bits.
Yeah.
But
okay.
there is a limitation. It's just that by chance, based on construct, right, even parity check codes allows me to detect, while not guaranteed, an odd number of bits. But I'm guaranteed to at least detect 1. Is that clear? It's a limitation to it. I'm just going through a code that you're familiar with to illustrate that.
Okay. Makes sense.
Okay. So what are the 2 codes I want you to be aware of? Okay, number 1 is called the cyclic code. Okay, the cyclic code leads us to something known as CRC. Okay, where the whole idea with the cyclic code is actually very interesting. Is that if you left shift the code, meaning that if I have a code that's 1011.000 and I left shift it, which means I move this 1 MSB position from the MSB position to the LSB position, then I'm going to get 011.001. If I can left shift this, and this is also a linear block code, okay, then what I have, right, obviously now is a code that has in fact R greater than 1, which means hopefully higher error detection capabilities. Okay, so how do I look at that? I'm going to now represent, instead of using the same data words, so the same 4-bit data words, 000 all the way through to 111, but instead, right, of just adding 1 parity bit, I now have to add some extra redundant bits, because I want to satisfy this property known as, right, the cyclic codes. Which means if you look at all of these codes, if I left shift them, so 0001011, if I left shift it, it's going to get 0010110, which is actually the next code. If I left shift this guy, right, it's going to be 0101100, right? So I'm going to look for the code that's actually 010, right, 1100. So this code, if I left shift it, becomes this code. But in any case, the left shifting of any of these codes here in a 7-bit code word is always going to result in another code word. But because this is also an LBC, which means I can now detect the daemon of this code by scanning through the entire code here and look for the code with the minimum number of 1s. What is the minimum number of 1s in these codes? Anyone?
3.
3, which means error detection capability?
2.
2?
Exactly. So this code now, because I've added more redundant bits, now guarantees me to be able to detect a little bit more than I otherwise can do so.
Up to 2 errors, right?
Guaranteed up to 2 errors.
Yeah.
But I've used 3 redundant bits though, right? So my code rate has gone down. Does that make sense? Right?
Yes.
I'm less efficient in the transmission of this code.
More unneeded bits per se, but
Mhm.
to detect more error possibilities.
That's right.
Okay.
Okay. So efficiency has gone down, but I've increased my so there's no free lunch, right? In order for me to be more robust, obviously I have to set more redundancy. But if I just want a simple quick check mechanism, right? Maybe parity code suffices. Okay. So the question now is, how do you generate this code? How do I take a data word and generate the CRC code? And that's your question 2, right? In assignment 3. Either question 2 or question 3, one of those. Okay. So the idea behind it, right, is simply this. Okay. What I want to do now, right, is I'm going to take a look at this code here and I say, okay, I want to generate from the data word to the code word. There are a couple of pieces of information that you actually need. Okay, it looks complex, but it's really not. Okay, it unfortunately requires you to refresh if you remember something known as long division. You guys remember long division? I think you were exposed to long division in grade 2, right? Something like that, grade 2 or grade 3.
In decimals, not in binary though, to be honest.
Right, but in binary, we're going to use something known as modulo 2, long division.
Are we going to do an example together?
Yes, we're going to do that. Yes, I'm going to do that
Yes,
for you right
that
now.
would help. That would help.
Okay. So the structure of which simply says this, because I need to do a long division, I need to know what the divisor is, right? And there's a divisor that is going to be shared between both the receiver and the sender. Okay, so I'll give you an example, right, of how we actually create that. Okay, in this example, right, I want to use and transmit the data with 1001. Okay, I want to produce the code word for transmission. And I know the divisor is given to me as 1011. Okay, so let's use the deck of slides. So I'm going to walk you through this illustration here. Okay, get this thing in position. So I have a data word that I have, right, which is 1001. Okay, the divisor, right, in long division that I'm going to use, and this is known to both the sender and transmitter and the receiver, and the divisor is now 1011. Okay, how CRC generation works, and you're going to be doing this in your assignment, and I want you to practice quite a bit because CRC is a very important technique, very much in use today, right? Because obviously of its somewhat simple way of generation. Okay, so the first thing I do is that I'm going to take 1001 and I'm going to try to divide into 1011. Does everybody follow? I'm going to do long division, but in modulo 2 long division. The first thing that you do is that you always augment, right, your data word. And you're going to augment by 1 bit less than the size of your divisor. So in this case, if the divisor is of length 4, I'm going to add in 3 zeros to it. Why? Because remember, right, this is the data word. Okay, and my goal is to ensure that I am able to divide the last bit of the data word at the same length with respect to the divisor. So if there's 4 bits in the divisor, I need to use 4 bits to divide into the divisor. So I always augment, right? Remember, the data word is what I'm trying to protect. So I always augment, right, the actual data word by a certain number of zeros to achieve this, right? 1 bit less. Then modulo 2 long division may sound sort of like complex or whatever it is, right? But it's actually very, very simple. It only requires you to do 2 operations, really. Check the MSB of the 4 bits you want to divide into, right? So I should use a different color. Check the MSB. In this case, it's a 1. If it's a 1, then I'm just going to take a 1 times the divisor, which is 1, 0, 1, 1. 1 times anything that's 1, 0, 1 is anything, right? Then I'm going to do an exclusive OR between these two values instead of subtraction. Right? Exclusive OR 1 and 1 gives you 0. Exclusive OR 0 and 1 gives you 0. 1, 0, 0, and then 1, 1, and there's going to be a 0. In fact, in most cases, right, we don't actually write out the first, because the first one, because we're matching the ones, right, the first one is always going to be a 0. Oops, not this. Oh, I don't have an eraser here. Sorry. Okay, there we go. Does everybody follow today? The first thing I look at is if this is a 1, then I'm going to take a 1 times and I'm going to do an exclusive OR. Then I take down the next bit, right? So I'm going to take down the next bit, right, which in this case, right, is now this guy here, 0. Because I always have to divide by 4 bits. Now, in this case, the MSB is 0. So I'm going to take a 0 times that. 0 times anything is 0. So I'm going to take the exclusive OR, 0, 0, 1. Does everybody follow? Then I'm going to take the next bit down. It's a 1. So I'm going to take a 1 times 1, 0, 1, 1. It's going to result in 0, 1, 1. Right, because this is exclusive OR. Take this down. This is a 0, 0, 0. 0 here is going to 0 times that. It's going to be 0, 0, 0, 0. Exclusive OR is going to yield me 1, 1, 0. Sorry about the space. Does everybody follow how I got to 1, 1, 0? Is anybody there?
You're going too fast. Can you slow down a bit, please?
Okay, where did I lose you?
I'm just trying to follow with what you're doing. You're just going too fast. So maybe just a couple of seconds, just to match up the speed. That would be great.
Okay, so is it clear at least through here?
No. Actually, one step behind the last one is very clear.
Okay, so this I did an exclusive OR. So this gave me a 1, 0, 0, right? And I took out another 0, which is giving me this. And then I did another 1 times of this.
Significant is 1, yeah, and then put it pretty much the same.
0, 1, 1, right?
Yeah, and then
0.
Drop down the last 0.
Exactly.
0, so put 0 there.
Yeah, this is all 0, so it's going to be 0, 0,
Yeah.
0, 0. So if I take the modulo 2 of this, it gives me 1, 1, 0.
Yes.
Okay. The nice thing about this is now I'm going to give you a couple things. Is that this, in fact, is R. Like your remainder in long division. Remember in your long division there's a remainder?
Yes.
In your long division. This is your data word. True? This is the original data word. I said 1001. The code word is nothing but the concatenation of the data word and the remainder, which means the code word is 1001
110.
110. Where this is K and this is R. So what does the receiver do? So the sender transmits this. The sender transmits this. The receiver will take this and divide this into this.
Again, the receiver will do what?
We'll take this 1001 110
Yes.
1001 110 and divide it by the same divisor, which is 1011.
Yes.
If this results in all zeros, then no errors detected, which means a syndrome of 0. If this results in a non-zero, then errors
there is an error. Yeah.
There's an error. Okay? So I want you to practice, obviously, the technicalities of this. And the question is, why does this work as an error checking mechanism? Remember, right? If I'm doing long division, if I tell you, right, what is the value to be divided by, If I tell you and you already know what the divisor is, and I also tell you what the remainder is, have I given you almost everything about this long division?
Yes, I can build the code word now on my own.
Exactly. With the exception of one thing, because there could be some ambiguity, right, of this value.
Well, I can take whatever word you give me, devise it, and then know if it's
Exactly. Whether or not you achieve.
there's an error or not.
Exactly. In fact, the idea behind modulo 2 arithmetic in terms of CRC is that you actually know 3 out of 4 pieces of a long division. You know the remainder, you know the divisor, and then you know what the data word is. So if you can check and realize that, you know what, with the remainder, that there is no additional remainder, then obviously there's no errors. Right? Now, obviously, this could go wrong, true? In transmission, or this could go wrong in transmission. Then obviously, this is not going to yield zeros. Do you follow?
Yes.
Okay. So don't get too many. It's not difficult at all, but I want you to understand is that it's really nothing but long division. Okay. And what this long division really, oops, that's not what I want to do. I'm going to share the screen again. Okay. What I have is simply, right, I'm going to take a long division and create the code word, which is nothing but the data word itself plus the remainder. At the receiver, right, this is just a blip on what sort of exclusive for is, but you should know that by now, simply takes this uncorrupted data, 1001, do the long division 1011. If it's all 0, no corruption, or at least no detected errors. If there was a corruption, which means initially it was 1001 becomes 1000 110, which means I receive this. And if I divide into the same divisor, I'm now going to get a non-zero remainder, which means the syndrome is not 0. Because the math is not going to add up. Because I've changed the value of what I'm dividing by. Right? So yes, you know, it's a bit of long division, but it's actually long division in a very interesting way, because this operation of exclusive OR is a very simple operation for computers. So if you have ever learned computer architecture, the ALU units, and so on and so forth, right? Exclusive OR operations are simple logic gates to achieve. So it may be more tedious as a human to do long division, but for a computer, it's an extremely efficient, right, sort of computational task. Any questions on CRCs? Any questions on CRCs?
I guess it's more clear now, because that was just when I was doing the question free, when I was reading the notes, I simply did not understand which first of all, I didn't even know which direction I should start with.
Right.
And then basically, and also the augmented ways of doing it, because I was a little bit confused. The code word or the word that was provided in the question was pretty long.
Right.
So I was not really sure if I should augment it into as what you just showed here.
Right.
So I guess right now it's more clear that I should start with on the left and then augmented it to find out the code word and stuff.
Right, exactly.
Okay.
So the idea is, obviously, because I haven't really taught you the technique, right? So if you had sort of pre-read it, right? But that's a good attempt, because now, right, with that pre-work that you did, right, it clarifies where you might have gone wrong in the application of the technique. Okay.
Right.
And obviously the goal is to learn it so that you can work on the assignment, right, and produce obviously the CRC, right, as necessary. Okay. But there is one limitation of CRCs. Okay. And I'll tell you what the limitation is that the problem with CRCs is this, is that the code word that I transmit, right, in this case, the code word here, 1001110 that I transmit, is a function on the length of the divisor, because the longer the divisor, the more R bits, the longer the code word. Does everybody see that? Because remember, I said I want n to approach infinity, which means for n to approach infinity, right, is that I need to use very long divisors. So very common, you'll see divisors like CRC15, CRC31s. That just means 16-bit divisors, 31-bit divisors, and so on and so forth. The problem with that is this, is that the code word that is generated, which is the concatenation of the remainder is always going to be 1 bit smaller than the divisor. Which means if this was CRC31, the remainder is going to be 30 bits. This makes the code word very long, potentially very long, right, to add more protection. Now, in most fixed bit width environments, we use something known as the checksum. Okay? The checksum simply says this. You can create an error detecting code of any length and still result in a fixed bit width checksum. Okay? And the checksum is exactly what I just told you in the example that I started the class. If I want to transmit something to Bob and the values are 1, 2, and 3, well, if I just blindly send 1, 2, and 3 to Bob, he's not going to have any idea if there was an error with it. But if I tell Bob, hey, I'm going to send you 1, 2, and 3, and the last value I transmit to you will now be, obviously, right, the sum of the values, which means I'm going to give you 1, 2, and 3, and 6. Bob now has a reference to determine if there was errors. He may not be completely right, because obviously I could have intended to transmit to him 2, 2, and 2, and that would have still been 6. But again, as I said, right, it's better than having no, right, error detection mechanism at all. So if checksums was that easy, right, meaning that I take a message, break it down into a certain number of bits, sum it all up, result in an n bits, right? What are the complications with checksum? And there's only really one minor complication, right? Let's assume, and go through this example first. Let's assume I want to transmit the values 7, 11, 12, 0, and 6. Does everybody follow here? 7, 11, 12, 0, and 6. Okay. So there are 5 numbers. They're all 4-bit values because they all range between 0 and 15. But in addition to transmitting these 5 numbers, I'm also going to tell Bob, hey, Bob, expect a 6th number from me. And the 6th number is the sum of all the 5 numbers before it. So if I add 7, 11, 12, 0, and 6, I'm going to get the value 36. The question now is this. Is 36 still a 4-bit value?
No.
Exactly. Why? Because if you start to add up fixed bit width values and multiple of them, it is very likely, with high probability, that in fact you're going to have an overflow condition. True?
Yes.
I mean, that's just by fact that it will overflow, right, if you're adding multiple fixed bit width values. So if you remember Comp 1113, right, there's something known as one's complement addition, where there is something known as n around carry. This is how, and this is the only thing. So the idea behind checksum is very, very simple, adding up the sum of all the values. But because it has a potential to overflow, we will use something from sort of a discrete math, right? And what we're going to do is we're going to do one's complement addition, right, with n around carry. And it simply says this. Okay, well, 36 is nothing but 32 plus 4, right? So the sum of these values, which is 36, is 100, 100, because it's 32 plus 4. I'm going to take and break this into 4 bits, which is the target bit width at a 1, and then take the overflow bits of 10, oops, which in this case, right, and add it to the value. So 100, 100 is going to get broken out into 2 chunks. The LSB 4 bits, 0100, and the MSB 10, 2 bits. And I'm going to add the MSB overflow bits to the LSB 4 bits, which means I'm going to add 0100 to 10, which gives me 0110.
Can you repeat that last part again, please?
Yeah, I can show you what I do here. Okay, on the whiteboard. It's probably easier.
Yeah.
Okay. So I know that if I add up a certain number of values, right, in this case, right, it's going to end up with 36. Okay. This 36 value is going to be 100100 in binary. True?
Yes.
This is 6 bits, but I wanted to have 4-bit values. True?
Yes. So
then
I'm
what
gonna
I
add
do,
two zeros at the end.
no, I'm going to break this down. I'm going to break this into two parts. I'm in fact going to do end around carry by moving this and adding it to this value, which means I'm adding the remaining 4 bits with 1, 0. And this is going to be 0, 1, 1, 0. This is the sum in 1's complement.
Yes.
Anything that overflowed. And then the checksum, right, is nothing but the complement of this value, which means what I transmit is 1, 0, 0, 1. Okay, so in the example, right, I'm adding up 7, 11, 12, 0, and 6, right? So I'm adding up 7, 11, 12, 0, and 6. That gives me a sum of 36. In binary, right, it's 32 plus 4. This is 1's complement that I do here. This is the sum. The negation of this sum gives me what's called the checksum. So this is the sender. This is what you transmit. The receiver adds up, right? So the receiver adds up 7, 11, 12, 0, 6, and whatever this checksum is. This is 9, 8 plus 1. And go through the same process with the end around carry, find the sum, take the complement. If the syndrome, which means if it all adds up equals to 0, 0, 0, 0, then no errors. If it's something that is non-0, 0, 0, then you have errors. Is that clear? Right? If I go back to the slide, so I can show you exactly. So I've basically just rehashed the slides for you. Right? If I add it all up, I add up and the sum is actually 6. But that's just the sum. That's not the checksum. Because the process, right, of transmitting the checksum is to say, okay, break it down 16 bits, add it all up, do 1's complement, and then complement the sum. The complementation of the sum is what I'm doing here. I'm complementing the sum. Then I send this, which is the checksum, with the data. So then what I have, right, as I transmit it, right, is that now I'm going to transmit 7, 11, 12, 0, and 6. But the complemented value, which is 9. This is 9. 1, 0, 0, 1 is 9. Right? So I'm transmitting the value 9. And what I have now is this. Transmit this value. Receiver gets all of these values, 7, 11, 12, 0, 6, and 9. Do, again, 1's complement summation. That gets me to 15. 15 in 4 bits is all 1s. And if I complement it, it's going to give me 0. So the same thing as what we did with CRCs. If the sum, right, in this case, at the receiver adds up all to 0, then it's no syndrome, and therefore no errors detected. Any questions on these problems? On checksum, sorry. So I don't want you to get too bogged down with the actual summing of values, because obviously you can use a calculator, you can do anything. I want to at least know if you are clear with what the process is. That there's really just adding of the sums here that you see here, right? This is adding of the sums here, 7, 11, 12, 0, 6. Okay? Gives you the value of 6. The complement of that value in 4 bits is 9. The receiver takes whatever it receives, including the checksum, which is the value of 9 now, gets the sum, complements it. If the result of that is all zeros, then there are no errors detected. If the result is non-zero, then there was an error detected. Are there any questions?
So are we required to actually understand and know how to not understand? Sorry, like actually like do it?
Yes, of course.
Okay.
You should be able to add 5 numbers, right? Well,
So 5 numbers, and then so like I kind of lost you at the 1 complements.
oh, the 1 complement is nothing. It's just a technique to say if there's an overflow, I'm going to wrap around the summation.
Oh, okay.
That's all there is. I'm taking this overflow bits and adding it up to the remaining 4 bits.
Oh, okay.
That's all there is. It's simply, as I said, think of the example I said. If I'm going to send you the values 1, 2, and 3, there's no way for you to detect errors. But if I'm going to send you the values 1, 2, and 3 and the value of the sum, which is 6, is there a better way for you to detect errors?
Okay.
But the problem, though, is this, is that because I'm adding up multiple values, practically, there could be a potential for overflow. And if it overflows, you do once complement and around carry. So that's what question 3 on the assignment is for you to actually compute, right, the checksum of any value. And it doesn't matter what base you use. You can compute the sum in binary, you can compute the sum in decimal, or you can compute the sum in hex.
So if we go back to the slide and we got the received checksum is 9, and then you said sum in 1's complement is 15.
Right.
So how is that going to be achieved? So what do you do? Now I have the 9 in binary, and then what?
No, then you convert all of these into binary, right? You can add 7, 11, 12, 0, 6, and 9.
Yes, and then I have the checksum, and then do what?
No, then you have the sum. Right?
I'm not following.
Okay. So what you want to be able to do here, okay, let me show you.
So, okay, I understood the sender's process into getting that packet with the checksum.
The receiver process is exactly the same.
So now I have 9, the checksum.
Yeah, so so if I have 7, 11, are you seeing the screen?
Yes, yes.
0, 6, and then 9, right?
Yes.
Okay.
Yes.
In binary, if I convert this, okay, this is going to be 0, 1, 1, 1. This is going to be 1, 0, 1, 1. This is going to be 1, 1, 0, 0. This is going to be 0, 0, 0, 0. This is going to be 0, 1, 1, 0. This is going to be 1, 0, 0, 1. True?
Okay, and add all those up?
If I add all this up, right, this is going to be 1, 0, 1, 1, 0, 1. Right?
Yeah.
Because it's 36 plus 9, which gives me 45.
Yes.
Okay. Now it's 6 bits. So I do n around carry. I plus 0 here. This gives me 1, 1, 1, 1. This
complement.
This is the F, this is 15, which is F in hex.
Yes. Negate. It's going to be 0.
And then exactly. Then I negate it because this is the sum. I want the checksum is the negation of this. This is going to not produce this.
Makes sense. Oh, the exact same process. We just do the exact same thing again.
Exactly.
Okay.
Okay.
Makes sense. Yeah.
And if the syndrome is 0, then you have no errors.
Chian, I have one question.
Yes.
On slide 10.38.
Yeah.
So we're sending the 4-bit number, 5 4-bit numbers, 7, 11, 12, 06. What if we send 60 4-bit numbers? Then
how many 4-bit numbers?
60 4-bit numbers.
Yeah.
And each of it is 15.
Yeah. Yeah.
Then the binary number will be 9 digits total.
Sure.
And
okay.
What should we add to the right 4 bits?
Yeah. So let's assume you have 9 bits, right?
Yeah.
So there's 4, 4, 4. So the first thing to do is, okay, there's 9 bits, right? Okay.
Actually,
so you
10
split.
bits, yeah.
Okay. So then you have 4 and 6, right?
Mm-hmm. Yeah.
You first add this 6 bits to this 4 first.
Okay.
Then you're likely still going to get possibly 6 or 7 bits. True?
Yeah.
The result of this, right, because it's going to overflow again, right? Depending on what it overflows, it will minimum be 6 bits, or it could be 7 bits, right? So let's assume it's 7 bits, then you're going to get this. Then you're going
do
to add,
that again.
yeah, and then you're going to, until you get to a 4-bit value.
I see.
Very good question, okay? Because the overflow could be more than one and around carry, which in this case, right? So if you ended up having 10 bits, then you get 4 plus 6. The 4 plus 6 is going to likely result in 7 bits. Then you have 4 plus 3. So you end around carry 3 bits here until such point you do not overflow.
Okay, makes sense.
Okay, no problem.
Yeah.
Okay. So then the next thing that I want to cover is to bring you an introduction into framing. Okay, and in fact, framing is very, very, very simple. Okay, if I can sort of get you to context switch a little bit here, right? And I want to sort of expose you to framing to sort of wrap up today's lecture. Okay. Remember, right? Error detection is one major component of the data link layer. But the truth is this, right? All of these bits have nowhere to go unless they have some kind of a header associated with it that tells it what the MAC ID is. And because MAC IDs, as we know, are minimally, right, 48 bits for each of the sender and the receiver, which means you're tagging on at least 96 bits of information. Okay, so then the question is this, is that, okay, how do I frame and why do I need to frame? Okay, so what is framing? Well, framing simply says this. If I have a variable size frame, which is what most of my frames are because they're not all in fixed size, I need to delineate the start and stop of each frame. So I'll give you an example. Who has dealt with something known as CSV files? Anybody has dealt with CSV files?
Yeah, with Python.
Exactly. Okay. Why do we have to have a comma separated value? Why?
To know the beginning and ending of each value?
Exactly. Because each of these values can take on a different number of bits. True? Because if they're all 32-bit values, then I can simply say this, right? If they're all represented in 32 bits, I should say that. Then just count the number of bits and you know where the next value is, right? The first 32 bits belongs to the first value, the next 32 bits belongs to the next value, right? And so on and so forth. But if they're all variable size, which means, yes, right, I can count to 32 bits, but I'm only using 8 bits for the first value, 12 bits for the next one. The only way I can compact my representation, right, is to now say, okay, I'm going to use 4, 8, 12, 13, whatever it is, but I'm now going to separate each of these values by commas. And that's what comma separated values are. In the data link, right, because we're also trying to do variable size frames, then what I want to be able to do, right, in particular, right, is to be able to indicate the start and stop of the frame. And the initial way of doing it is actually very, very simple, right? If I have all of these bits and sort of characters that I'm transmitting, in the early days when we transmitted data, they were all characters, that were all ASCII 8-bit codes. It simply says this, right? And if you guys have seen ASCII codes, right, the 8 bits, which means I have a total of up to 256 combinations of ones and zeros. There must be one code representation that I can do that simply says this. Okay, if I have variable size code, right, is there a way for me to find one code that does not map to a character? Which means all the characters generated in the past was simply keystrokes of a keyboard or combination of the keystrokes. And the total number of combinations are less than 256. So there must be one bit representation in 8 bits that is not mapped to one of these characters. Then what I have now, just like I chose the character, the comma, right, which is in the CSV, to be the special character, which means the commas don't appear in your data. Then the first occurrence of this comma is going to indicate the start of the frame. And then the second occurrence is going to indicate the stop of the frame. So now, it doesn't matter how many bits there are in my payload. The first time I hit this unique flag, it means that's the start of the frame. And the second time I hit this flag again, it tells me the stop. The third time I hit it, it's the start. The fourth time I hit it, it's going to be the stop. So in fact, I've just used this unique character, right, and in CSV files it's the comma, to indicate between different frames. Okay, So the issue is this, was that when you're only transmitting characters, that was a very simple problem to solve. But then you guys started to transmit things like audio and video associated with it, where now the uniqueness of 8 bits is no longer guaranteed, because we know from the PCM process, right, depending on the sampling and the quantization, right, something that was unique in representation is no longer unique. So what do I do? Well, I can do something known as character-oriented, but with byte stuffing. The idea is very simple as well. It says this, okay? But this is a very inefficient process. It says this, okay, I'm now going to obviously have the flag that can potentially happen in my data. I'm going to now preempt this data, right? Because I know it's actually the data and not the flag by another special character, and I'm going to choose the escape key. But there's also a possibility that, in fact, this escape key, because there's no uniqueness to this data, could also be in the data. So at the end of the day, my goal is to say this, okay, I'm still sticking on to my 8-bit unique flag. But anytime there's a flag in the data, I'm going to preempt it with an escape. Anytime there's an escape, I'm also going to preempt with an escape. And I said this is really inefficient because now, potentially, right, I could be down to 50% efficiency, because if my entire data stream was escape keys, then I need to preempt every escape key with another escape. So I'm in fact telling the receiver, hey, the first occurrence of the escape key, that's my indicator to you that the next character you must keep, because that's data. And then the next occurrence of it, it's telling you that the next escape character, right, is the data, and so on and so forth. So while it's true that I can get away with a mechanism of sorts, this suddenly become inefficient, right? Because of the number of bits that I insert. And not only that, right? The idea behind it is that, yes, it's simple for me to insert and it's simple for the receiver to remove because I have indicators here. But it's a very inefficient mechanism. And not only that, our codes are no longer 8 bits. Because of the fact that, you know, Melody wants emojis, emoticons, right? And whatnot that you guys use, right, to represent pizzas, you know, and so on and so forth. Our codes are now 32-bit Unicodes, which means each of these additional characters that I insert are now 32 bits at a time. There we go. Okay, so more and more becomes longer codes, more and more efficiency. What we do now, so byte stuffing is or character-oriented type of framing is essentially, you know, sort of obsoleted now. Okay, what's taken its place now, right, is simply that we are going into something known as bit-oriented framing, and there are 2 changes to it, really, on how we actually frame, while trying to preserve the uniqueness of the headers and the flags. Number 1 is that the data that we look at no longer has to be in boundaries of characters. Like, remember, in this case, right, we're always looking at character at a time. So either these are 8-bit ASCII codes or 32-bit Unicodes, but we're looking at them 1 character at a time. The idea is, why do we need to have these boundaries? And the answer is we don't. In fact, I can streamline this by saying that the entire data is nothing but a string of 1s and 0s. So all of a sudden, I don't have 8-bit boundaries and I don't have 32-bit boundaries. All I have left is very simply a string of 1s and 0s. And now I can go ahead and, in fact, and create a delimiter of any pattern that I want. And my goal is, obviously, that it may show up in the data, but I want to preemptively destroy or indicate that this flag that exists in the data is actually data and not the flag. So I still want this, right? The first occurrence of 0 followed by 6 1s, right, which is the flag, indicates the start of the frame. The second occurrence indicates the end of the frame. But because this flag can happen also as an 8-bit stream as part of the data, my goal is to preemptively indicate that in the data. And the mechanism to do so is very, very simple. Okay, if I take this string of 1s and 0s, which is the data now, okay, effectively, right, if I know that the delimiter is 0 followed by 6 1s and a 0, I want to prevent this from ever showing up in the data stream, even if it doesn't. Because remember, right, I'm looking at this data. You're looking at all the bits at a glance because you're a human. But as a computer or as a networking device, you're receiving them one bit at a time, which means you don't know this whole stream, but you're receiving 0, 0, 0, followed by 1, followed by 1, followed by 1, followed by 1, and so on and so forth. So you're getting them one bit at a time. So you don't see the entire sequence of data bits like you would see here on paper. So what happens is this. In order for you to preemptively make sure that this pattern doesn't show up in part of the data, you start scanning. Obviously, you get started by this pattern and say, okay, it's the start of the frame. And I look at my entire payload. Oh, there's a 0, which means that there's a potential that this could be data, right, that is showing up as the flag. So then that's followed by a 1, followed by a 1, followed by a 1, followed by a 1. I'm getting more and more close to being the delimiter. At the end of the 5th one, irregardless what the remaining bits are, I'm going to blindly insert a 0 because I cannot wait for the next one to show up. Because if let's say I go 0, 1, 1, 1, 1, 1, which is 5 ones, wait for the 6th one to come by, insert a 0, I effectively created the delimiter. Okay, so blindly, right, what I do is this, is that I insert a 0 after I've been triggered by 0 and 5 consecutive ones. Because the next time a 1 comes by or a 0 comes by, which I do not know what will come by, I'm preemptively destroying the pattern. And that the receiver is the same exact process. I get triggered by a 0, count 5 ones, and then remove the 0 that I know the sender inserted so that I can retrieve the entire data sequence, right, from the sender and the receiver. And that's what sort of framing is all about, is that we've started with character-oriented framing, where uniqueness of the characters can be preserved because we are creating characters either by keystrokes or combination of keystrokes. That mechanism broke down because of the fact that we started to transmit audio and video, where now these characters are no longer unique because of PCM and so on and so forth. So what do? I go into a very sort of inefficient mechanism of doing what we call byte stuffing. But the overhead became essentially potentially too large. So we moved on away from sort of character-oriented and we move into bit-oriented, right? Where now all what I do is I look at all of the data stream as a string of 1s and 0s, create a unique flag that I'm looking for, and all I do now is preemptively ensure that if this data, right, contains the flag, I'll preemptively break it by inserting a 0 after 5 ones occurs in sort of the payload that was triggered by a 0. And then the receiver does the same blind operation, right, to do so. And that's all there is to sort of the framing that I want you guys to be aware of. Okay? Any questions on framing? Okay, so as we move along in sort of what we have covered so far, okay, the big thing that we did today obviously was error detection and correction. Okay, things like sort of framing is really just an auxiliary sort of a fixed protocol type thing that we have to deal with because we have to delimit between frames, right? But the key thing I want you to take away, right, which will likely show up in your quiz next week, right, a very, very big hint, right, obviously is something to do with, right, error detection and correction. Okay, that is something that you will want to be able to exercise, right, in addition, right, to just data communications, because in your coding, right, that you do, right, you might want to incorporate error detection codes. Every time you download a very large file, right, there is always a verification of the download. Right, and obviously, right, the verification of the download, right, could be one of, you know, the many different error detection type of codes that we built into the system. Okay, so it's 1 o'clock, right? I want to sort of end the lecture here today, right? The only reminder I have for you, at least for this week, right, is that your quiz next week, obviously, right, will cover up to the material today, okay, which is the end of framing, okay, slide 11.7. Okay, but the important thing that I want you to sort of be able to get through, right, is obviously error detection and coding. Okay, that's probably the more important part of the lecture today. The second thing, obviously, is that now you are able to complete, which is really just the exercising of two techniques, CRCs and checksums, and that will allow you to do question 2 and 3 and complete the assignment. It is not due Monday, but obviously it will be due on Wednesday. And any questions that you have, right, please obviously send me an email, right, and we'll address that on email. Okay.
One more question, if possible.
Yeah, go ahead.
Are we going to have any future assignments other than the final project after this one?
Yeah, you have a fourth assignment. I've already said there are 4 assignments and a project if there is no final exam. So the number of assignments hasn't changed because obviously this assignment only covers up the material that we covered today, right? And we still have 2 more full lectures to go with. So there will be another assignment for you guys to work on. And look at the assignments as practicing the techniques that are actually taught in class, which is what they really are. Okay, Rana?
Yep, thank you.
Okay, so I'll stay behind for a few more minutes, right? If there are no other questions, right? Thank you, everybody. Okay, have a great week. It's going to be a sunny week, right? So do lots of work, right? But at the same time, right, get some sun.
Thank you. See you next weekend.
Yep, see you guys.
Thank
and girls. Okay, thank you, everybody. And I'll stay online for a few more minutes if there are any questions. Oh, Melody, are you going to show up at 2:30 again at all, or no? Okay, so if you show up, then I'm going to let Richard know that you might be joining. And I can have both of you, right, maybe illustrate and show your depiction of a spot prompt at the beginning of class. And it'll just be like 2 minutes, right, just while we wait for everybody to get online. He's actually a very good artist, actually. And I'm not a very artistic person, but I'll leave for the class to judge, right, who has a better depiction of the spot prompt. Okay, and we'll do that for like 2 or 3 minutes just to sort of get the class started. Okay, Melody, are you okay with that? Okay, so I'll see you. If anybody wants to join at 2:30, by means, right, just feel free to do so, right? If you want to hear the lecture a little bit again, right, the different portions of it, right, by all means do so. Okay, thank you, everybody.
That's what I was going to ask.
Yeah, who's this?
Yongju.
Yeah, again, I've always said, right, if you want to listen to the lecture again, by all means, show up in the class again to listen to it.
Perfect, thank you.
Okay. Right, and then I'll see some of you next week and some of you at 2:30.
Thank you.